Greetings, everyone. Dr. Pryor here, ULM Chemistry 1007. Thank you for tuning in again. Just to finish up, we're working on Chapter 8 right now, and we're going to get into covalent bonding. Many of you may have saw this in your high school chemistry. This is Gen Chem 1. We do have the final coming, and there'll be more details, as I've mentioned in other videos. Covalent bonding is where atoms share electrons, and they share valence electrons. They don't share core electrons, they share valence electrons. And there are several electrostatic interactions in these bonds. And previously, we talked about ionic bonding, where electrons are completely transferred from one atom to another atom. But in covalent bonding, electrons are shared, so all the unique forces need to be taken into account. We have the electrons, which, for example, there are several electrostatic interactions in these bonds. We have attraction between electrons and nuclei. The nuclei have the proton positive charge, electrons are negatively charged. We have repulsion between electrons. We have repulsion between nuclei. So it's a fine balance to whether a covalent bond even occurs, right? It has to be energetically favorable, like everything that we see. It has to have a reason to exist, and we explain that through energy. So for a bond to form, the attractions must be greater than the repulsions. When we get into molecular orbital theory, we'll get into anti-bonding orbitals that contribute to the molecule not existing, and we can do a calculation and figure out if the molecule should not exist, like helium-2. When we do molecular orbital theory, we'll find out between covalent atoms that form covalent bonding that helium-2 does not exist under normal conditions because of the anti-bonding orbitals cancel out any stability gained by the bonding orbitals. And this is really getting us to that point. So we can see here how the nucleus, the protons repel each other, the electrons repel each other, but the electrons attract to the nucleus and the nucleus attracts to the electron. So there's a lot of forces going on. To determine what happens, we need to know some more things. Lewis structure, well, we'll get more in depth, but let's just look at this. And we know that this here is it's got two electrons. Any single line that you see is always going to have two electrons. So this contains two electrons, right? Any bond between two atoms is representative of two paired electrons. Remember what we learned earlier about orbital theory? The most you can have is two electrons in any orbital. Well, you can imagine this is a molecular orbital formed between two hydrogen atoms. The same with chlorine, although a little bit different. The energy is different. There's more electrons involved in chlorine, but we have this bonding, these two electrons that bond to form diatomic chlorine. So again, this is how we would write it. Hydrogen has no lone pair of electrons, but chlorine here has lone pairs of electrons, three lone pairs of electrons in atoms, in each chloride atom in the molecule. And again, how many electrons are in this bond here? It's the same as with the hydrogen. There's two electrons. That is what keeps these two atoms together, and it's a covalent bond. Now, the number of bonds for nonmetals. Remember, oxygen, hydrogen, carbon, all of these are nonmetals. And hydrogen and fluorine are both nonmetal atoms. And fluorine has in the p orbitals 5 electrons and 2 in the s. And it really only needs one more electron to be happy, and it gets it from hydrogen. And hydrogen needs only one electron from fluorine. So they end up sharing an electron. Water shares 2 bonds with 2 hydrogen atoms, and it achieves an octet because we got to always remember that the shared electrons are attributed to both atoms. The shared electrons are considered to belong to fluorine in this case, and the shared electrons are considered to be given to hydrogen. Now, the lone pair electrons are only on fluorine, okay? And we'll do other calculations where the electrons have to be divided in two and given to each atom, but not in this case. Not in this case. For the octet rule, we can consider the electrons belong to both atoms and count them as such. So there's 2 electrons that belong to hydrogen, 2 electrons here that belong to oxygen, plus another bond, which is another 2 electrons for oxygen. And then 2 lone pairs, which is 4 electrons, gives us 8 electrons to meet the octet rule. Now, nitrogen is P3, and it needs 3 more electrons to be happy. So it makes 3 bonds with hydrogen and has 1 lone pair of electrons, and it meets the octet rule that way. We can say 2, 4, 6 electrons in shared bonds with hydrogen for nitrogen, and then 2 electrons in a single lone pair. And then we have carbon, which is the favorite among organic chemists. It has 4 electrons. Hydrogen has 1, so it needs 4 hydrogens to donate an electron to its 4 electrons in its valence shell. It's in group 4. Carbon is P4, excuse me, or P2 maybe. And we have carbon and hydrogen to form methane coming together. Lone pairs are always by themselves, and they are a feature of that atom, not the molecule all the time. But we will find out there are resonances where lone pairs can also contribute to the molecule. That's in resonance structures. But right now, hydrofluoric acid, the lone pairs on fluorine, we have 3 lone pairs of electrons, which means we have 6 electrons and 3 lone pairs, are all owned by fluorine. Hydrogen has no part in taking, or as this hydrogen has no part here in interacting with this. Although another hydrofluoric acid molecule could have hydrogen bonding between this fluorine, such as it's one of fluorine, nitrogen, and oxygen can all hydrogen bond. And so there would be a slight interaction between hydrogen and fluorine between intermolecular forces, right? So there is hydrogen bonding in hydrofluoric acid. The same with water. Water, of course, has hydrogen bonding, and so does nitrogen. Ammonia can hydrogen bond with other ammonia molecules and water if it's dissolved in water. Methane cannot do that. Methane does not form hydrogen bonds because there is no polarity. Carbon and hydrogen equally share the electron, whereas we're going to find out that hydrofluoric acid, the fluorine gets the majority of the electrons, and we're going to find out in water that, or excuse me, that's written the wrong direction. We have the electrons going towards oxygen. We have the electrons going towards oxygen, so oxygen gets the majority of the electrons, and nitrogen gets a slight bit more of the electron density than hydrogen, but not by much. And then carbon and hydrogen is quite equal. There really is no polarity between carbon and hydrogen. So we can put these together by drawing Lewis dot structures of individual atoms. And we also need to keep track of how many valence electrons these neutral atoms have and add them together when they come together to form a molecule, such as carbon dioxide. We know there's 6 electrons in a neutral oxygen species, another 6 in another one, and then there's only 4 electrons for carbon, which come from the 2s and the 2p orbitals. 2 electrons in the 2 electrons in the p orbital and 2 electrons in the s orbital. We eventually fill that up, and we get 8 electrons by moving these electrons around, and we get double bonds. So we have 4 electrons here. We have another 4 electrons here, which adds up to 8. So carbon has 8 electrons. And so we have 4 electrons that also belong to oxygen on top of 2 lone pairs, which is another 4. So we have 8 electrons for oxygen, and the same with this oxygen. So guess what? We have a molecule that meets the octet rule and is very stable. Carbon dioxide is quite stable. We could draw the Lewis dot structure of a nitrogen atom, and we could do that with the second nitrogen atom, and it has 5 electrons around it, and it comes together to form 3 pairs that are shared between nitrogen. So we end up getting a triple bond, which is very short, very closer together than this bond is shorter than this double bond, and the double bond is shorter than a single bond, right? Um, so we have single bonds, double bonds, and triple bonds. We saw single bonds on the last slide with methane. Double bonds we see here with carbon dioxide, and triple bonds we see with dinitrogen gas, diatomic nitrogen, which is in the atmosphere, which is very unreactive. And these bonds are short and hard to break. The triple bonds take a lot of energy to break. The polarity of bonds and electronegativity. Electrons in a covalent bond are not always shared equally um, because electronegativity, we've already studied that, and we've looked at electron affinity and ionization energy. All these things are linked together because of the shielding effect, the valence electrons being shielded by core electrons or not, and the proton charge that is positive that attracts the negative electrons to it to some degree. So in a nonpolar covalent bond, the electrons are shared equally. There is no one atom getting more electrons than the other atom. Think about a shared household where the kids get equal amount of gifts, right? There's no bias, or it could be a household where one kid gets more gifts than the other kid, which can cause trouble. But in polar covalent bonds, one atom gets more electron density than another atom. So it pulls the electrons to itself with greater force because it has greater attraction for the electrons than the atom that it's in a bond with. Polar or non-polar covalent bonds. Okay, let's look at a diatomic that's it's made here. It's made of just fluorine, and although fluorine is very electronegative, um, two fluoride molecules in a bond together have no more have no more power to attract the electrons than say the other species. So each fluoride attracts the electron equally, even if it's more powerful than say hydrogen. So the electrons, there is no partial charge on this on diatomic fluorine, but we could have a weak acid called hydrofluoric acid, and it's the only weak acid of the halogens because it holds the hydrogen so tightly it cannot deionize and break away to give up protons. It's held very tightly. And part of the reason is the electron density goes towards fluorine, as the red shows. And all the electron density relies to the fluorine, although there is a little bit of electron density remaining with the hydrogen. So it's not completely an ionic bond yet, but it does break up almost like an ionic bond. So it's very close to being an ionic bond with hydrofluoric acid, but it isn't. Lithium fluoride, on the other hand, that's another story. Lithium fluoride, the electrons are way over here with the fluoride. In fact, they get completely pulled over to lithium fluoride. Lithium loses its electron, fluorine gains electrons. So there is no line to draw between lithium fluoride. There is no lithium fluoride. There is no polar covalent or covalent bond here. Okay. So if I were to try and draw a line between these two, that's wrong. There is no sharing of electrons. Ionic compounds, we don't draw lines between them. Of course, if we drew fluoride out, we can draw a covalent bond between fluoride, and that is quite accurate. We can do that, and there's two electrons shared by the fluorine molecule, the diatomic fluorine molecule. Okay, so electronegativity. That increases from left to right. So electronegativity increases this way, and electronegativity increases going up the columns, right? Or if we draw the diagonal, electronegativity increases that way. We use the Linus Pauling electronegativity scale. Remember the Linus Pauling electronegativity scale that we used on test 4, and we could figure out the difference in electronegativities. And some atoms are very high, some are very high medium, some are just medium, and then some have low electronegativity values, and we can calculate the difference, the electronegativity difference between an atom involved in a bond, and figure out if it's ionic or covalent. And the higher the electronegativity difference, the more likely we have an ionic compound. The lower the electronegativity difference, the more likely we have a covalent compound. And if we're right in between, we might have a polar covalent bond where the electrons are shared, but the electrons are shared unequally, and one atom gets more electrons than the other atom. Here's the case of a polar covalent bond. There is a partial positive charge that they like to use. That's partially positive because the electrons are pulled predominantly towards fluorine, and there's a dipole that exists towards fluorine. And we're going to look at a mathematical way to sort of calculate that. And we can look this up in tables. But electrons tend to spend more time around the more electronegative atom. It's fluorine in this case. Hydrogen is more partially positive because it sort of loses its electron, but not completely, at least not until it ionizes. When it ionizes, it loses its electron and becomes a proton as a weak acid. What we just saw was a polar covalent bond. Hydrofluoric acid is a polar covalent bond, but hydrochloric acid, hydrobromic, and hydroiodic acid will end up being strong acids and almost act completely like an ionic bond. Depending if they're in water or not, it depends on some things. But notice if the bond length is smaller, it's more likely a covalent, polar covalent bond. But if the bond length is very long, it's more easy to break. So this is more like almost like an ionic salt. So this is hydrofluoric acid is definitely polar covalent. And so we can look at hydrobromic acid and hydrochloric acid as long as we don't throw it into water immediately and it's in a purified form, a concentrated acid solution. It would sort of look like a polar covalent bond until we throw it into water. So these are very unique. Electronegativity differences increase, are very much different here. So you see it decreases as these atoms get bigger, right? Fluoride is smaller than chlorine. Chlorine is bigger than fluoride, but bromine is bigger than chlorine, and iodine is bigger than bromine. And as they get larger and larger, it's harder. Hydrogen stays small, so it's hard. It's very difficult for the bonds to overlap. These are difficult. These are polar covalent or even almost ionic-like. We have dipole moments, and the dipole moment increases as the atoms get smaller, and as fluorine also is more electronegative. So the dipole is very strong with fluorine, less so with iodine. The problem with hydroiodic acid is iodine is so much bigger than hydrogen, it hardly can overlap, and it's very inefficient overlap. So it's very difficult for a polar covalent bond to stay together. It breaks up in water quite easily, like almost like it's an ionic compound. It's a strong acid, hydroiodic acid, where hydrofluoric acid is a very weak acid because of the small sizes of fluorine and hydrogen and the overlaps of orbitals. So if we wanted to look at a dipole moment, we could have a negative charge and this positive charge right here of any ionic species. We could just make it a simple diatomic, a diatomic example, and we can calculate the dipole moment, which is expressed as U. So when two electrical charges of equal magnitude but of opposite signs are separated by a distance, a dipole forms. Okay, so this is a polar covalent bond, likely. We don't know until we do the calculation, but it's likely a polar covalent bond, and one atom gets all of the electrons and the other atom loses some of the electron density. So we draw to the atom that gets the electron density, or excuse me, this is a reverse. This is a reverse, my fault. The electrons are pulled towards the negative species, and the electron density lies on this side. The electron density is towards the negative side because it gets the electrons. It has a greater electronegativity as an atom, which is a feature due to the shielding effect and all the things we talked about. And that would be like fluorine. This would be like fluorine, for example, and this would be like hydrogen, for example, right? And so we could put fluorine as having a partial negative charge and hydrogen having a partial positive charge. And so we also have this distance, and it's not really radius, but it starts from the nucleus and starts from where the nucleus is. So it's called R, but it's really like the interatomic distance. It's not quite the radius, but it is started from the center of the atom. And you can measure that with special equipment and you get some angstrom value. So as the radius goes up and the Q goes up, your dipole moment can go up, and you can determine that in dipole. So as the charge goes down and the distance goes down, the dipole decreases. So you can play with this mathematically. And so with ionic compounds, it's a complete transfer of electron. But if it's a covalent compound, the electrons are shared. But then as we go from covalent, we can start to go to polar covalent into the ionic world, and the electron could be completely lost. So we use electronegativity differences to guide us. If the electronegativity or the change in the electronegativity is greater than 2 when two atoms come together, it's likely ionic, and it means if it's greater than 2, the electron is not shared, it's not polar covalent, it's actually ionic. Exceptions exist, for example, like metals that are highly oxidized. There's these interesting ligand formations with metals, and it can have all sorts of unique ligand formations, and we can do complex coordination chemistry and inorganic. And if you take Gen Chem, you'll get some of that. You'll learn some really cool things, maybe about um, crystal field theory and all these cool things. Or if you take my um, uh, inorganic class. Also, look at the physical properties of the compounds. You'll find out that covalent compounds have lower melting points, say, than ionic compounds, right? And so that's just one feature of ionic versus covalent bonding. And that brings us to the end. I thank you for listening, Chemistry 1007 students. Please keep pushing forward. The final is close to being upon us. I want all of you to do great, and I will see you in class.